When we are assessing a predictive model, we care less about how well it fits the data, and more about how well it predicts future data. In other words, metrics like R-squared are less useful, and instead we need to measure how closely the predicted y values match the actual y values. There are a number of different ways of measuring this difference. The difference is the error, and the ways of measuring it are called error metrics. However, most models will do relatively well at predicting the y values of the data that they were trained on. After all, that's kind of the point of fitting the model. However, they will do worse at predicting the y values of new data that they were not trained on. The error they make on these new data points is called the generalization error. It measures how well the model's predictions generalize to new data. The question is, how do we get new data to measure the generalization error on? What we have to do is split our dataset into two portions, the training set and the test set. We will build the model and find the optimal values of its parameters on the training set. Then we will use that model to predict the response variable for the test set. However, as we know what the true response variables are for the test set, we can measure the generalization error of the model on the test set. However, the situation is actually a little more complicated than the simple picture on the previous slide suggests. Typically, we don't just fit a single model and have done with it. We often want to tweak aspects of our model to improve it. For example, maybe we try different combinations of the explanatory variables. However, if we do that and measure the generalization error on the test set each time, then we are essentially using the test set as an extension of the training set. We cannot get a good idea of the true generalization error on the test set if we are also using the test set to optimize certain parts of the model. Our model will be optimized for the test set data, and so the test set will give us a biased generalization error and make us think that our model is better than it really is. So what do we do? Well, we actually need to split our training set up further into a smaller training data set that we actually use to train the model, and then a validation set that we use for measuring the prediction error as we experiment with different variants of the model. Finally, when we've found the best variant on the validation data, then we can measure its generalization error on the test set. However, there's another problem. As we keep on chopping off portions of our data, we have less and less of it to train the model on. But predictive models generally get better at making predictions when we train them on more data. There's a solution to this problem too. Instead of having a fixed division between training and validation data, we actually rotate the validation set around in the training data. This is called cross-validation. The most common method is known as k-fold cross-validation. We divide the training data into k pieces, and if, for example, k is 5, then we split it into 5 pieces. We train the model 5 times. Each time we train it on a different 4/5 of the data, and validate it on the remaining 1/5. The final validation error for any model is the average of the validation error on all 5 of these individual cross-validations. Here is an illustration of k-fold cross-validation. As you can see, by rotating around the validation portion of the dataset, we are able to train the model on the entire training dataset. So if there are some unusual data points in one part of the training data, we will not miss training the model on them. However, we still have to keep a separate test set. After we've found the optimal version of the model using the validation set, we can then measure the true generalization error on the test set, using data that the model has never seen before at any part of its training. So let's review the steps of creating a predictive model. First, we always need to separate the data into training and test sets. After we have done so, it's important not to look at the test set again. No visualization, no analysis, no peeking. The only thing we use the test set for is measuring the generalization error at the end. Then we follow our standard data science methodology and do some exploratory data analysis on the training data. Visualizations, summary statistics. The idea is to get a sense of the variation in the data, which variables might be most useful for prediction, and what kind of model might work well. Step 3. Pick a model. This is often driven by the type of data that we have. For example, if we are trying to predict a continuous y variable, we will need to use a regression model, such as linear regression. Then we find the best version of our model using cross-validation, and once that is done, we can measure the generalization error on the test set. If your generalization error is low enough, you may decide to stop here. However, sometimes you may need to do better, and so you'll go back to an earlier step in the process and create a new model. Finally, once you have trained a predictive model that you are happy with, you can do something cool with it, such as recommending the next TV show to watch on Netflix, or predicting who will win the Super Bowl, or making money on the stock market.